So how much guys are you enjoying this semester? Well, this semester is a very special one, because of the pandemic. We are doing our lecture online, and even the exams actually were totally different. And I believe you guys are learning something very new throughout this totally new process of untact business, right? We are doing untact business. Well, I think it's time to think about the final exam, and I hope our final exam is also very special because for the first time and the last time, we'll meet each other in classroom, and that'll be really really fun for the final exam. So final exam will be in class exam, all right? And the coverage is mostly from my own lecture. Okay, you don't have to read too much of the textbook. Just take a look at the note you guys actually took from my lecture. So the final exam will be on June 18th. I believe it's next Thursday, 2020, and 7 to 9 p.m. Sorry for the late time, because there were so many different students in my class with different schedule and needs. We tried to find the time slot where everybody can actually come to the class. All right, and the place is somewhere in the building 301. At the end of this class, we're gonna announce the place through the Kakao Talk. Well, the coverage, everything. Remember, last midterm exam was like a report up to something like later part of conduction, but this time in the final exam I would like to cover everything, starting from conduction, convection, and the radiation. Regarding the radiation, I haven't covered the contents yet, but from next lecture, I would like to cover everything pretty quickly. And my lecture is the most important material for your final exam. So take a look at your note and study your note, all right? Anybody who attended my class, pretty much every class, will have no problem solving these problems. Okay, so please focus on your class note. All right, and final exam will be closed book. Because it's only for 2 hours, there's not much actually contents that we can provide you for you to solve these problems open book. It's gonna be too much complicated. So it's just a short amount of time. I'd like to evaluate how much knowledge you guys observed from me in this class, and how much actually capability you guys obtained in terms of thinking in a higher level inference scheme process. All right, so the exam will be also, even though it's a closed book, don't be worried about memorizing equations and information. Okay, all basic information, equations if needed, and information will be provided whenever it's necessary. Okay, so don't worry about memorizing the things. Don't care about this too much. There's of course question. I'll provide anything you like. Okay. So it's a closed book, but it's much more like an open book. All right. But again, the exam problems will be mostly, I say mostly, directly from my lecture. So these are the incentives to the ones actually who attended my lecture consistently. Okay, those who missed my lecture a lot will have a lot of trouble solving these problems. So no need to memorize. Just on that, understand my lecture. Try to understand. The high-level inference schemes. The high schemes. What could be the example? Example could be something like analysis, right? Sorry, not analysis. Analogy, right? Analogy between momentum transfer, heat transfer, and material transfer. What are the same approach that you can apply for all these different problems? What are the differences? No, you think in a actually higher level. Okay, this is not just a mathematics class. So be able to. I'm going to ask you to explain physical interpretations regarding the thermal problems. All right, and finally, well, you have to use professional language in your answers. So master the language. I remember I stressed a lot about the use of professional language. Master the language of dimensionless number. These are the words that we use to communicate with each other, dimensionless numbers. These are the words that actually we understand how this physics is actually working regarding these number problems. Okay, so master, make sure that you master the dimensionless numbers. What are their physical meanings? What are their roles in the solving equations? How we arrive at such kind of the dimensionless numbers. Mostly we arrive dimensionless numbers by normalized analysis. Just by taking normalization steps to the given equations, even without solving the equations, we were able to arrive at the precious dimensionless numbers. Okay. All right. I think I talked pretty much about the final exam. Okay. So if you have further question, you can ask me. At the end of chapter 8, we have to master the concept of laminar flow in circular channels. circular tubes. In this case, you have a tube like this, okay, with circular cross section, diameter d, all right. And when you do the analysis, we always take a small patch of an element, all right, and we provide the coordinate system x, and because it's circular, instead of y we use radial direction, so we use r coordinate, all right. Yeah, and then we take this little element, okay, and this little element has dx, dy, and so on, dr, and so on and so forth. And if you take a look at this element, there's the heat going in, qr, by conduction, and heat moving out by conduction, qr plus partial qr, partial r, dr. And as heat changes, temperature on the left hand side and the right hand side also changes, partial t, partial x, tx, and temperature changes y direction as well. If you take into account all these components, all these elements, well, so go through the derivation process appearing on your textbook, okay, and you'll arrive at this final equation, which is Nusselt number regarding the diameter of this tube or the pipe will be just a constant. This is really nice result, 4.36 in case surface convection is constant, okay, and 3.66 in case surface temperature is constant. The problem of deriving this final results is highly probable that I'll actually ask you guys to derive the equations in the final exam. So bear this in mind, okay? Please practice. Just read your textbook and practice of your own regarding how you can derive this condition. And I'm sure most of you guys can easily do that. Anybody who took my lecture, there's no reason why you cannot understand it. It's a very, very simple concept. Just try it, okay? But in your final exam, you have to demonstrate that you'll be able to do this. Okay, let's move on to free convection. The situation is completely different from what we have learned so far. So far, the flow was forced to be driven from one point to the other with certain velocity, for example, u infinity, right? And in this free convection, the flow is not driven by the just the pressure gradient, but by body forces. Well, why did this body force occur? Because of density gradient. Okay, so now we are thinking about the physics. How did we, understand the physics? From our daily lives, right? In your daily lives, you experience this, experience that, and you know how this, density changes. Why does density change? Well, and in an effort to support your understanding further, in your department, the School of Mechanical Engineering, maybe the other departments, provides the experimental courses. Then you obtain more understanding about how this physics works. All right? Anyways, throughout that process, we know how the density changes. Why? Because of temperature. Density is a strong function of temperature. We'll see soon how that affects. And because of this, the forces are generated, and we call such force buoyancy force. Buoyancy force. You know how you actually float in the water because of buoyancy, right? And why does this buoyancy, occur? Because everybody lives on Earth. What does Earth have? It has gravitational force. The famous gravitational forces pointed out by Newton as the force proportional to the multiplication of two masses and inversely proportional to the distance of these two masses. We still don't understand, how this gravitational field is actually associated with the other kind of fields like electric field and magnetic field. Einstein tried to understand everything in one unified approach. He didn't still achieve the final understanding. Final understanding will be very important, right? Because if you understand that how these gravitational forces and other fields like electric field and magnetic fields are associated, there might be a way of actually shielding these gravitational forces, like the same way we shield the electrical field and magnetic field. We can shield the electric and magnetic field, right? But not the gravitational field. If you can shield the gravitational field, well, Star Wars is right there. You can levitate and travel around. We haven't achieved it yet. You guys will achieve it sometimes. But before that, yes, we are interested in the heat phenomena. All right. There could be two kind of different cases. One could be, well, for example, you have this object. It's a cross section, long and thin wire. Heat it up, and that will create the buoyant flow to the higher direction. And that will create some flow like this. Everything will, move up, float up, in other words. And there could be a flow profile like this. All right. 1, 2, 3. 1, 2. And what's interesting about this flow is that, well, there will be T infinity, but there will be some temperature inside this flow profile, and that temperature will be normally higher than the ambient temperature, which is at quiescent state. Quiescent, I say quiescent. The calm state, right? Why is quiescent state, we say, because the velocity in the ambient area normally zero, right? Well, it might not be zero. We'll discuss that. And there will be certain kind of density around it, but because temperature inside this profile is higher, because this is the happen to be hot wire. You heat up the wire, you look at the cross section, it'll actually create the high temperature surrounding around this wire, and as temperature goes up, density will become lower, and that lower density will create buoyancy force around it. And that's because of that this flow occurs, and because of that flow around this velocity profile will follow this flow, and we call this plumb. Okay, plumb. There could be the other case where you have for example, the source of flow, and flow is just coming out, but then because of the gravity again, and because this flow is happen to be have higher temperature than surroundings, there will be flow going up, as it does also drags the quiescent flow around it. The quiescent flow, T infinity quiescent, U infinity will be zero, the rho infinity. Again, the rho here will be lower than the surrounding. Rho will be lower than the surrounding because temperature will be higher than the surrounding. And of course, the gravitational flow is directed towards to the center of the Earth, center of mass. We call this flow buoyancy. Buoyancy jet. Look, there's a jet coming out, but because of buoyancy, it will continue to travel upward. All right, these are the phenomena that's highly complicated, and normally engineers rely upon their experimental analysis. But before that, we'd like to have some intuition into this phenomena through our analytic understanding. That's what we have done in the previous chapters, right? Analytic understanding first, and then experimental understanding, spoken in language of the analytic understanding, right? So what's the simplest analytic understanding that we can have about this problem? It is nothing but the hot plate facing upward, heated up hot plate so that there will be flow above the hot plate. Okay, so you guys have a hot plate like this. Because it's hot, there will be flow going up, and it will go something like this. There will be flow profile because surface temperature will be higher than the quiescent temperature. And you can assign the coordinate. This time this will be y direction, and this will be x direction. And this distance, because within this layer you have a laminar boundary layer. Okay, outside the infinity will be normally zero, right? So you have outside rho infinity, and of course the gravitational field is downward. And because of this flow also is associated with heat transfer, which we call conduction, right? Transfer. Right, conduction. And temperature profile will look something like this. So as the temperature profile changes, in other words, surface temperature is higher and the surrounding temperature is lower, and so we call this surface temperature, right? Ts, isn't it? Is everything visible? And there will be again this thermal boundary layer, right? And y, x, and there will be T infinity, rho infinity as well. Okay, we call this hot vertical plate. Well, in the whole scenario, what's important is that, well, we have to assume the incompressible flow, otherwise the problem becomes very complicated. Yet, we mentioned that, well, density changes. Is that really incompressible? Not incompressible, but still, you just assume that it's incompressible, but only the density will be affected. Okay, how is it affected? Well, normally it's inversely proportional to the temperature. The higher the temperature you have, the lower the density you have, because of what? Volume expansion. Volume expansion, with the same mass, density will go down. Okay, that's what happens here, right? And here you take a little element again, and everybody's now well educated about this approach, I believe. And there will be shear forces, right? Tau plus partial tau partial y dy. And think about the shear forces, right? That is acted upon this little element, and you can set up a nice momentum equation right here. How does it look like? Now everybody's familiar with this. F equals to ma. Where does this F come from? Two things. First of all, by the shear balance, right? And right here, the new forces that you need to think about it is actually buoyancy forces, right? The buoyancy force will actually drive this little element as well. How is the buoyancy force? Well, first of all, what is the shear force? That will be mu partial square u partial y square, right? The pedal plate. You can think about if you pull the pedal plate, there will be shear force that will drive the liquid motion. And buoyancy force is nothing but gravitational constant times density difference. We learned this from high school physics. Everybody's familiar with that. Because of density change, buoyancy force will occur, to y direction, right? Sorry, to x direction, right? The positive x direction, positive x, positive x, positive x direction, upward, because gravitation is downward. All right. So that is the driving force. These two forces are driving forces. F equals to ma, the mass represented by the density, because it's a small element and the volume will be cancelled out. And ma, acceleration, right? Time change of u. By using the chain rule, you will be able to drive this. Right? Again, this is the consequence of the chain rule applied to partial derivative with respect to time. All right? So in a different way, you just divide everything by rho. This will be g rho infinity minus rho over rho plus mu over rho dynamic viscosity partial square u. Can you see this? Partial y square equals to the same thing, u partial x plus v partial u partial y. So the difference from our previous derivation process was this term, driven by the gravitational field, and density difference is actually one of the key driving forces of this motion of this little patch element. Okay. So now you understand that if you have a very concrete understanding about physics, you can apply such understanding to the mathematical model, right, in a proper way. Then come up with different kind of equations. This is exactly the process that you guys will follow in your future career. You guys are engineers, okay? You have to have an understanding of physics, and you have to apply such kind of understanding to the equations, okay? in a proper way. I say proper because sometimes you need to disregard certain terms. You need to think about more about certain contributions. So you are the engineer at the center of this decision. That is the essence of higher level inference scheme that you guys learned from this heat transfer class. Okay. Again, you need to have a basic understanding. Well, what is that? Well, how does this density difference occur? Because of the thermal expansion. Okay, you guys probably already learned this kind of things from your freshman physics course and thermodynamics class, right? And we call this volumetric thermal expansion question. Again, this is just a simple representation of our observation of physics that's going on around us, and that is nothing but, for example, beta, which is nothing but normally minus the change in the density. We put negative sign because we want to have beta as positive coefficient, right? And normally if temperature goes up, density will go down. It becomes negative. That's why we put negative sign here to compensate for it. And it is delta rho over rho, the change of density per the original density. The relative change, right? Not the absolute change, right? Like the same way we understand the stress and strain, right? What is stress? It is nothing but the force normalized by the surface area, the cross-section area. What is strain? It is the length change normalized by original length. So this is much more like the strain. Okay, we have to have a fair understanding of all these things. Per temperature change, delta T. Okay, and in physics, for example, we use, for example, partial derivative of this 1 over rho, delta rho over delta T, partial rho and partial T. Well, when the pressure is constant. The pressure is constant. Okay, so if you just plug in the numbers that you know, the variables that you know, minus what is delta rho? Rho infinity will be higher. The surrounding, the quiescent state has lower temperature, so it has more packed material. Rho infinity minus rho. Inside this flow profile, density is lower. That's why this, the flow stream is occurring. Rho is lower right there, and delta T is, well, T infinity minus T. Well, T is higher than T infinity, so it's fair to write down rho infinity minus rho over rho T minus T infinity. This way we can make everything positive. Okay, everything positive. Because T is higher than normally T infinity in this case. Okay? All right, so if you take a look at this equation right here, you can take a look at this term, which is exactly this term, isn't it? So we can switch the variable. Rho infinity minus rho over rho is nothing but beta times T minus T infinity. Okay, so you can just put beta here, beta T minus T infinity. So your equation becomes something like this. G is clear. Beta T minus T infinity plus do partial square u partial y square. The momentum driving force by the shear u partial x plus v partial u partial y. Still, there needs to be the mass conserved because we assume the incompressible flow, right? So incompressible flow, mass consumption, sorry, mass conservation. So u partial y equals to 0. In thermal equation, well, we assume that there's no viscous dissipation. It's only the diffusion that changes the temperature. So this is like a driving force, right? The heat conducted in and conducted out, that change will actually give rise to the temperature change in the little element, and because of, again, the chain rule, you have this expression. I hope now everybody's familiar regarding this kind of approach, because we try this approach again and again many times in my class. And in your final exam, I hope everybody can actually describe things like this. Okay? Yeah, so in case we are talking about a gas, there's a beautiful law about this gas. That's ideal gas. So for an ideal gas, okay, so starting from now, we have to think about an ideal gas, right? Ideal gas, well, the density rho in the ideal gas is pressure divided by gas constant times temperature. All right? And because of this equation right here, beta, 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 this equation, now you can apply that equation, d rho over dt. What is it? So based on this, you can even calculate the beta, which is nothing but minus 1 over rho partial t. And because temperature is in the denominator, the whole thing will become positive, and the 1 over rho, and the p over r, they are just constant, but t becomes square in this case. And the p over rt is a rho, so rho cancels out, and the only term that's remaining is simple and powerful. Look, rho, in case beta, in case of the ideal gas, it's nothing but the reciprocal of temperature, 1 over t. Isn't that beautiful, right? But remember, in this specific case, this cannot be applied to liquid, only for the gas, like an ideal gas, all right? With this in mind, you can just keep progressing. For example, well, what's the next step? What was the next step that we have taken in our previous analysis? Yes, the similarity analysis. Similarity analysis. You would like to normalize the things. And it is such simple normalization process that teaches us about these precious dimensionless variables and the physical understanding behind all these things. So these are the things that I'm going to ask you in your final exam, okay? How did you arrive at such kind of numbers, okay? Even though you have a little problem in the derivation process, you might make mistake. That's not important, okay? That's not important. The way of your explanation, the way of understanding. So I'm going to ask you, for example, in your final exam, write down how did you arrive at this kind of dimensionless numbers. Even though your analysis might not be correct, you can still, describe such kind of process. Similarity analysis. That is a tool we use. Similarity analysis. What do? We define the normalized independent variable like x asterisk and y asterisk regarding a typical dimension, the length of this plate, for example. What about u asterisk? How do we define it? Well, u over u infinity. However, what is u infinity this time? Quiescent, right? 0. So there's no point of using u infinity here because you're going to be ended with infinity. So for the time being, why don't you think about certain kind of velocity, which we don't know, but later on we will define for the convenience of our expression. This is another totally different term, okay? So we assume that there might be some kind of number, and later on we take care of the number such that our expression becomes simple. In your final, for example, dissertation of your PhD topic or your report in your company, when you go out for the professional career, you would like to define some kind of concept which can be modified later on for a better understanding of the whole thing, for a simple understanding of the whole thing. This is the approach we'll take. We don't know what u0 is, but there might be some kind of velocity like this, and even v can be normalized by the same u0, because I'm going to use that. So we call this u0 the reference velocity, some velocity, okay, which we don't know yet. And t normalized will be like the same way before, t minus t infinity, ts minus t infinity. This way, at the surface, t will become 1, at the infinity, t will become 0. Okay, everything becomes simple. So if you just plug in all these normalized variables into your equation and then do a little bit of cancellation, right? Simple. I might ask you to do this in your final exam again. Okay? I might ask you to do, but I'm not going to go through it because we have, gone through this a couple of times already. Okay? There's no point of doing that again. You're gonna arrive at a very nice expression. Your momentum equation will immediately become Reynolds number like this: partial square u asterisk partial y asterisk square plus g beta t surface minus t infinity. Why do we have this? Because of this. Same thing, right? L. Why do we have this? Because of this. Remember? Over u0 square. Why do we have this? Because of this. Right. Simple. And t asterisk. On the right hand side, you have u asterisk partial u asterisk partial x asterisk plus v asterisk. These are the consequences of the chain rule. Again, partial u asterisk partial y asterisk. Right? Simple, right? Again, bear this in mind. I might ask you guys to drive this kind of things in your final exam. Okay? So practice it. I'm saying this, practice it. Well, at this moment, what's really interesting is that, well, why don't we choose u0 square same as this? What happens then? This whole term will become just a unity. Okay? That's what I mentioned at the beginning of this. Assume something which can be taken care of later on to make your expression simpler. This is another skill you guys can learn for your future career as an engineer. Okay? That's interesting, isn't it? If you do that, well, so u0 square, for example, u0 square, square will be nothing but g beta ts minus t infinity. Yeah, you can define it like this. Then your whole equation becomes very simple, right? Just become 1 over Reynolds and this whole term, this whole thing. I'm gonna use green. Becomes a unity. Isn't that beautiful, right? So same math, same calculation, but with your intuition about desire to drive the whole thing simple, you can come up with totally different result. That's what I'm saying, okay? So anyways, here, without this, the previous equation was like just this and this part in previous chapters. Because of gravitational force and buoyancy, this term appears in the free convection. Okay. And the other term that we use is simple, right? It's a thermal equation, and the consequence of similarity analysis is that Reynolds number, Prandtl number. So this equation is exactly same as the one we used to use before. I star square equals to u asterisk partial, sorry, t asterisk over partial x asterisk plus v asterisk partial t squared as a consequence of the chain rule, like this. I'm grading your midterm now, and I ask you to actually come up with explanation about your calculation process. Some of you guys just read out your equation, okay? That's interesting. What I ask you to do is this kind of explanation, right? For example, this term, where this term came from. Well, your language could be like this. Well, this is nothing but a time derivative of the, for example, velocity, which is nothing but if you multiply by the mass, it'll be momentum, right? Yeah. So time derivative, why does it look like this? Because of chain rule. I have asked you to actually come up with this kind of answer. Not many people actually did that. It's okay. Okay, just a midterm. Forget it. Now finals left. Okay, I'm gonna ask one more time the similar kind of questions in your final exam. Remember, okay? Please explain your equation in terms of your understanding about physical insight. Okay? That's really important. All right. So if you do this, what's interesting is that, wow, this term didn't exist before. And now it, came up to our business. What does it have? It has temperature in it. Remember, the momentum equation before had nothing to do with temperature. You could just independently solve this momentum equation. Now, not anymore. Okay? Why? Because temperature is associated with the density associated with buoyancy force, associated with the driving force of this little element actually taking the momentum transfer. Okay, so now this thermal equation and momentum equations are completely coupled together. Okay, before it was only thermal equation that was coupled to momentum equation, but now both are coupled together. Very interesting, very interesting. Okay. So anyways, if you choose like this, u0 square Then this whole term becomes the green area, green box becomes a unity, and also Reynolds number, which is nothing but remember U0L, right, over nu. This is the only velocity available for this Reynolds number. It used to be U infinity, right? Now it's U0, right? And because U0, your choice was like that, just plug in right there and see what happens. Square root G beta Ts minus T infinity times L, well, and times L over nu, which is nothing but square root G beta Ts minus T infinity L to the cubic over, I would like to, make this all in square root over nu square. Okay, what is it? This becomes this number anyways, and we can define the Reynolds number here, square, with this definition in mind. In particular, it's nothing but G beta Ts minus, a little bit complicated, but I'll tell you the reason why. Nu square. Okay, that's Reynolds number square. And in particular, this Reynolds number square, when we define the velocity like this, we call this Reynolds number square GL. We call this Grashof number, named after scientist Grashof number. Remember, this is dimensionless number. Why? Because Reynolds number is dimensionless number. Dimensionless square is dimensionless, right? And Reynolds number is the ratio between the inertial force and the viscous force. Again, in the final exam, probably I can ask you like that. What is the definition of this number? In terms of thermal phenomena. Explain it. Okay. Things like that. So rather than too much of a calculation, expect that I will ask you guys a lot of concept questions, okay? That's why you need to look at your previous note and then imagine what I have told you regarding this conceptual understanding. That is more important. Of course, there will be calculation, there will be some application problems that I might ask you, okay? That's just a little part, okay? There might be, okay? But mostly I'm going to ask you concept questions. So Grashof number, this dimensionless number stands for the ratio between, what is this term? So buoyancy force, right? It stands for viscous force. So this is nothing but the ratio between the buoyancy forces to the viscous forces. So now we have a new definition, Grashof number, which is nothing but the square of the Reynolds number with particular definition of the reference speed. Remember, particular definition of reference speed. And this Grashof number represents the ratio between buoyancy force and the viscous force. When the buoyancy force becomes important, Grashof number will become big. When the buoyancy force can be negligible, it will be negligible or zero. For example, if you go to the orbit of the Earth, what is the gravitational constant there? When the Elon Musk team took the rocket and went to the orbit last week, what was the gravitational force there? Zero. sometimes this gravitational force can actually show up as different aspect. It might not be gravitational force, but accelerational force, for example, that should be taken into account. Centrifugal force, for example, that needs to be taken into account because these are the body forces. Okay? I'll talk about something very important, very interesting later on regarding this different way of understanding the forces. Okay? So if you do that, well, Reynolds number is nothing but square root of Grashof number in this case. So your equation will become like 1 over Grashof number L square root partial square U star partial Y star square plus, remember, the term in front of T asterisk became 1 by the definition of the special U0 square, right? And the remaining terms are the same. Sorry. Asterisk plus, make it neat, write neat. X asterisk plus V. The consequence of chain rule, again, I'm talking about this million times, okay? And the other equation used to be the equation using Reynolds number, but now it became Grashof number by the new definition of U0 star, by the definition of the reference speed, convenient definition of reference speed. So T star partial Y star square equals to U star partial T star partial X asterisk V asterisk partial T asterisk partial Y asterisk as a consequence of applying the chain rule. I'll talk about this billion times. Nusselt number L. Well, if you calculate this, we speak in terms of Nusselt number. The language, common language we use in professional setup is a Nusselt number, okay? It's a function of what? Look, Grashof number, right? Grashof number of L and the Prandtl number. These are the parameters that we use. Now we change our gear a little bit. Well, if U infinity was not 0, well, then there's no reason why we cannot use U asterisk as a ratio of U over the U infinity, right? We use the U over U0 because U infinity was 0, but if the U infinity is not 0, then you need to think about this momentum term into the consideration. Alright? In that case, we're going to be ended with different expression. 1 over, oh, Reynolds number is still Reynolds number in that case, right? Square root U asterisk partial Y star square plus. Now you need to think about the other term, that's the Grashof number. Reynolds number to square T star. It's obvious. If you take a look at this term. This term is obvious, very simple. Okay? And the remaining term will be U asterisk, partial U asterisk, partial X asterisk, plus V asterisk, partial U asterisk, partial Y asterisk. Okay? This gives us really nice understanding about the physics indeed. This is the case where we have external velocity in the region we thought quiescent. It's not quiescent anymore, there's a velocity. And the internal flow is driven not only by the external velocity but also by the body force, which is the buoyancy force as well. Okay? So in this case, what really matters is the which one matters. inertial force or buoyancy force. You need to compare this. Inertial force dominating flow. Then this term, Grashof number over Reynolds number squared, will be very, very small. This is exactly the case that we have dealt with so far in our previous chapters of the convection. Remember, we never thought about gravitational field, we never thought about the buoyancy. Why? Because Grashof number is much smaller than Reynolds number squared. Because of that, this term disappeared. The coupling term to the temperature disappeared. Now, it cannot disappear anymore. Buoyancy, force, dominating flow. What happens? Look, Grashof number compared with Reynolds number is much bigger. Now you need to think about this equation right here. Right? So it really depends upon which phenomena is dominating. Okay? Normally, if gravitational over Reynolds number squared is about the same magnitude, then your solution will take into account both effects, flow effect or momentum effect and buoyancy effect, and the ratio between these two, right? Momentum diffusion divided by thermal diffusion, that's Prandtl number. Again, I'm going to ask you what the Prandtl number is in your exam. Please be prepared to be able to explain. Again, I'm going to ask you to a case when the Prandtl number is big, when the Prandtl number is small. How can you deal with our equations in these two cases? In the written form, okay? So be prepared for that. Please memorize, not memorize, please think about my previous lectures. Okay, so how can we solve this equation? How could we solve the other equations in our previous chapters? We use similarity transform, right? Because those equations were partial differential equations, impossible to solve. We would like to drive the equation into ordinary form such that even though we use numerical solutions, we can come up with much simpler approach and much easier approach to explain in numerical terms. Okay. So what do we do? We use similarity transform. So we define a single variable eta that represent both variables y and x. However, in that process, it's better to define using Grashof number in terms of x to the quarter power. In your final exam, I'm going to ask you why we define eta like this. I'm saying this, okay? Study it and try to come up with your own explanation compared with my previous lecture, because in my previous lecture I clearly explained why I defined eta in such a way. Now, in your final exam, I'm going to ask you why you define eta this way. And this way, I can evaluate how much concept you guys digested from my lecture. This way, I can evaluate how much you guys are prepared for applying the concepts you guys learned from my lecture for your future career. That is the most important goal of this education, isn't it? Okay, so again, be prepared to explain how you got this. It's a closed book. closed book, okay? Remember it's closed book, but the equations are given, okay? Okay. So as a consequence of this similarity transform, you will have ordinary differential equation, which will look like f double prime, triple prime, 3f, f double prime, minus 2, f prime square plus t, this is 0. And thermal equation becomes t asterisk double prime plus 3 prime number f t asterisk prime equals to 0. Should I ask you guys to derive this equation in your final exam? I don't think so. The reason is very simple. It takes such a long time for you guys to actually come up with this answer, probably. So 2 hours is not good enough. Okay, so don't worry, I'm gonna ask you guys this, but always remember this is in parallel to our previous derivation process, which is pretty complicated. Remember, we spent the whole lecture actually to derive this equation, but that was worth it, right? Yeah. So in your future career, probably you'll have chances to spend the whole night, spend your whole week, even the whole month to derive an equation. Be prepared for that. This is not for your final exam, okay? And as a consequence of solving this, again, I'm not gonna ask you this to solve. Simple, but takes a lot of time. That's why I wouldn't do that. So your solution will become like this, and g, the function of Prandtl number, is a consequence of numerical solution. There's no closed form solution. Okay, so in order to approximate this numerical solution, the engineers came up with the special equation which appears in your textbook. Okay, I'm not going to go through that. And finally, if you take the Knudsen number average, you can easily do that because of this fourth power. 4/3 Knudsen number. Okay, I can stop here. I believe we are pretty much at the core of chapter 9, and I will just quickly go over chapter 9 next time, and chapter 10, boiling and condensation, I'm gonna quickly go over that as well, and the remaining part is just the radiation, which requires a lot of mathematical skills, and I'll quickly go over. I'm sure I can quickly go over and deliver every details of this concept to you easily. Okay, that completes everything. So be prepared to learn this radiation as well, and condensation and boiling as well, because some part of this concept will be covered in your final exam as well. It's not going to be the major part, but I will surely ask you how you understood that. So basically, the message I deliver today is that in your final evaluation, I think that will be more important, because your midterm, as a consequence of grading, I see that everybody's doing pretty much similar level. Your final exam will determine your grade, precisely. All right. So study your previous class note. That's the very important thing to do. All right, thank you, and have a good week, and I'll see you this Thursday.